Hi everyone, I'm Alexandra DeLeon, the Content Coordinator for NVIDIA. On behalf of NVIDIA and today's presenter, Ian Stewart, Tegra Software Engineer, I want to welcome all of you to today's webinar, Get Started with the JetPack Camera API. All attendees will be muted during the webinar. However, you can ask questions throughout by typing them in the Q&A area provided on your screen, and we encourage you to do so. Ian will answer questions verbally at the conclusion of his presentation. We are recording this webinar and will make it available for download. You'll receive an email shortly after the conclusion of the webinar with a link to the recording and a PDF of the slides. So without further delay, here is Ian Stewart.
Thank you, Alexandra, and thank you to everybody who has joined us today for this webinar. NVIDIA's Jetson TX1 is the world's most advanced system for embedded visual computing, delivering the highest performance, the latest technology, and the best development platform. But Jetson would not be what it is today without developers such as yourselves who are continually pushing the limits of what is possible with the Jetson platform. Whether you're a hobbyist or a multi-billion-dollar company, NVIDIA is dedicated to providing high-quality development tools and APIs that enable fast and efficient development today, as well as the flexibility to evolve and meet the needs of tomorrow. Cameras play a key role in a visual computing platform, and so today's webinar is dedicated to getting you started with image captures and basic processing using Jetson and the new JetPack Camera API. Next. I'll be providing an overview of the Jetson TX1 camera subsystem. This will outline the tremendous capabilities of the TX1 platform and will provide context for some of the software features that will be introduced later. The majority of our time will be spent discussing LIBARGUS, NVIDIA's new C++ camera API for Jetson that is included with JetPack. This will begin with an introduction to the core API elements and design that form the foundation of Argus, after which we'll move on to a real example of a simple image capturing application that uses Argus. I'll be using an incremental approach along with diagrams, which should make it easy to follow along. We'll then expand onto the Argus basics to introduce events, metadata, and extensions which add on to the basic functionality of the core API. We'll tie up the Argus portion with a short discussion of performance implications to consider in order to write efficient camera applications to ensure you get every last ounce of performance out of Jetson. Since Argus is just an image capturing API, however, a discussion of Argus alone would only provide one half of the picture. Every Argus application needs some sort of consumer for the images it produces. And so I'll finish up by introducing a few consumer utilities and APIs that may be used alongside Argus to complete your visual computing and image processing applications. I have a lot to cover today, so I'll not be stopping to address questions until the end, time permitting, but I'm being joined by two colleagues, Brad and Peter, who will be available to answer questions throughout the presentation. If you have any questions, please ask them using the ReadyTalk chat interface, and one of us will get to them as soon as possible. Before moving on, I want to give a quick note on the use of USB cameras. That is, USB cameras do not utilize the TX1 camera subsystem or the LIBARGUS API being introduced today, and so USB cameras will not be covered in today's webinar. Access to USB cameras is still supported using the standard Video for Linux 2 APIs, and I have posted a link to this documentation for your convenience. So let's dive in and get started with an overview of the Jetson TX1 camera subsystem we'll be using today. The TX1 camera subsystem consists of three main parts. The first component, responsible for receiving image data from external camera sensor modules into TX1, is the CSI interface. CSI represents the Camera Serial Interface standard specification created by the MIPI Alliance Working Group specifically for mobile camera platforms. TX1's CSI is based on the CSI2 standard, which is the most widely adopted camera interface in mobile devices today. It offers a robust, scalable, low-power, high-speed, and cost-effective camera interface that supports a wide range of imaging products. TX1 provides three 4-lane CSI blocks, providing a total of 12 data lanes, each capable of up to 1.5 gigabits per second per lane, or 18 gigabits per second total. Each 4-lane block supports either a single 4-lane high-bandwidth sensor, or may be divided to support a single 2-lane or dual 2-lane sensors. A 4-lane sensor running at full bandwidth provides a 600 megapixel per second throughput limit, which is equivalent to 20 megapixels driven at 30 frames per second, while the flexibility to use 2-lane sensors provides for direct connection of up to 6 CSI transmitting camera sensors, all of which may be active simultaneously. Data coming in from the sensors through CSI is then sent to the video input, or VI unit. This unit formats the data into pixel streams suitable for memory storage or ISP processing before routing it to the correct destination unit. For example, a capture writing raw Bayer pixels to memory would have VI route the pixels directly to memory instead of processing them through ISP. For the sake of today's webinar, however, we will assume that all sensor data is routed through VI to ISP for processing, and so VI may be considered a pixel transport between CSI and ISP. Feeding the TX1 camera system are 2 identical yet independent image signal processors. These ISP units are responsible for 2 key tasks. The first is to take the unviewable raw Bayer pixel data captured by the sensor and convert this into a high-quality image or video stream that is pleasing to the human eye, while the second is to generate statistics about the image that may be used by the camera driver or a client application in order to adapt the capture settings to fit the environment in which the camera is being used. For example, histogram statistics may report an underexposed image, which could be understood by the application to mean that the exposure time or gain of the next capture should be increased. This diagram shows a simplified view of a typical Bayer input processing path and some of the features included within TX1's ISP units. From the left, raw Bayer pixels lead into early operations that help account for and correct physical limitations of the imaging sensor, such as by removing dead or stuck pixels, denoising the data using a low-pass filter, or by applying lens shading compensation to reduce vignetting effects due to non-uniform sensor illumination. This corrected Bayer data proceeds to demosaicing, where it is converted to tricolor RGB or YUV pixels, though image quality is aided once again by various sharpening and color artifact reduction routines that are applied. Finally, color space conversion, correction, and tone curve adjustments are applied to reach the final results. Downscaling may also be performed if needed. As I mentioned earlier, various statistics are also generated by the ISP throughout the process, which we can see being pushed to memory from each of the processing blocks below. In terms of capabilities, the ISP units on TX1 are each capable of supporting sensors up to 6,000 pixels wide, or about 27 megapixels, and provide an individual throughput of 600 million pixels per second, or 1.2 billion pixels per second combined. When you consider that this is equivalent to hundreds of billions of CPU or GPU operations per second, the benefit of not just one, but 2 dedicated low-power ISP units becomes clear. While every TX1 developer kit includes a 5 megapixel fixed focus reference sensor to get you started, the true draw of TX1 as an embedded imaging platform is the ability to create a specialized hardware package for the specific needs of your application. Leopard Imaging specializes in the creation of camera solutions, and as an NVIDIA scaling partner, they are capable of addressing a wide range of camera system needs specifically for the Jetson embedded program. Leopard currently offers 2 off-the-shelf sensors that work out of the box with the TX1 development kit. The IMX185, which is 1080p, and the IMX274, which is 4K, are the 2 sensors that are available today. Each sensor comes with an adapter board that plugs into the TX1 dev kit carrier board, and the current adapter board supports the use of up to 3 sensors. These devices are available for purchase from Leopard's website. Beyond this, however, Leopard's partnership with NVIDIA means that they are enabled with all the tools, hardware, and skill set required to create specialized solutions for your specific needs, covering the entire gamut from stereo depth mapping for machine vision applications to robust solutions for autonomous vehicles. That brings us to our main topic today, an introduction to the new Jetson Camera API included with JetPack, LIBARGUS. The image processing industry still lacks a camera API with low-level control of the camera sensor to generate the input image stream needed by cutting-edge computational photography and computer vision. That quote comes from the KHRONOS website, posted nearly 4 years ago, though unfortunately the quote is still true today. At the time, KHRONOS recognized this need for an open camera standard and began work on the OpenGL API, with NVIDIA being one of the driving members of this effort. Unfortunately, efforts were stalled and progress was not keeping up with NVIDIA's immediate and increasing need for such an API. So, NVIDIA took many of the OpenGL design concepts and, with KHRONOS' blessing, continued development in-house. While both the API and the name have evolved, Argus being the name of a 100-eyed monster from Greek mythology, which seemed fitting for a camera API, most of the core design goals and requirements originally set forth by OpenGL continue to lay the foundation for Argus. What are the Argus design goals? To start, Argus continues to target an open and standard API. NVIDIA did not create Argus in order to retain IP or develop proprietary technologies. On the contrary, NVIDIA continues to stand by our commitment to develop and support open standards that benefit the entire field of visual computing, hardware vendors and developers in particular. This is not to say that Argus is already an open standard, because it is not. But what it does imply is that we are approaching the API design in a way that we hope will meet the requirements of not just NVIDIA platforms, but all camera visual computing platforms to come. And if the time comes when other vendors would like to consider adopting an open standard, we'll be ready. To that end, you may notice that Argus continues to fit in very well with the rest of the KHRONOS ecosystem. That was not by accident. An obvious extension of being an open standard is that it should also be cross-platform. And in fact, this was one of the motivating factors for NVIDIA to create Argus. Our Linux support was previously lacking, and Argus was our solution to quickly bring TX1 camera support to our L4T platform. Beyond portability, Argus needs to be powerful enough to provide low-level control of the camera subsystem. This includes not just the processing inputs and controls, but also metadata outputs for the frame statistics generated by ISP or similar components. In order to provide low-level control and metadata on a per-frame basis, Argus uses a frame-based capture control pipeline. This means that each capture request provides the complete settings that are used for the capture, rather than maintaining state within a context or global object. Visual computing products are continually demanding more and more pixels, with multi-camera devices quickly becoming the norm rather than the exception. So Argus needs to be flexible enough to handle any configuration possible, through multi-stream, multi-camera, and even multi-process output configurations. When it comes to mobile image processing capabilities, nothing comes close to the power of TX1's Maxwell GPU. To enable simple and efficient interop with other APIs that provide image processing with the Maxwell GPU or other hardware components, Argus supports image outputs via EGLStreams. I will be talking a little more about EGLStreams later in the presentation. Finally, Argus needs to be ready for the future with an extendable design to allow growth and new feature development without breaking existing application compatibility. Argus is a C++ API and is contained within the Argus namespace, though I will be omitting this prefix throughout the presentation for the sake of brevity. While the use of C++ makes for a nice API, the embedded industry is often subject to strict coding restrictions, and so Argus has been limited to C++ 03 with exceptions and RTTI features disabled. Most fundamental design choice adopted by Argus is that all methods must be provided by interfaces rather than directly by object types. Besides providing a cohesive API through specialized interfaces, this design is crucial for the versioning and extension mechanism used by Argus, which we'll see shortly. Since objects do not provide methods directly, they should be thought of as opaque pointers or unique handles to API entities. Every object is capable of providing interfaces through inheritance of the interface provider base class. But objects are also divided into two subtypes, defined by how the objects are managed. Destructible objects must be created, owned, and destroyed by the client application, while non-destructible objects are children of other Argus objects, and are owned and destroyed by these parent objects. Interfaces, meanwhile, form the majority of the Argus API. They are pure virtual classes, always prefixed with an uppercase I, and are identified by a 128-bit universally unique interface ID. Interfaces are acquired at runtime from an object that supports it, and once the interface has been acquired, it will remain valid throughout the lifetime of the object that returned it. The next point describes the fundamental versioning and extension system used by Argus, and that is that interfaces do not change once published. Rather than modify existing interfaces, which would introduce incompatibilities with previous versions of Argus, any additions to the API will be done via the addition of new interfaces. This ensures backwards compatibility with existing Argus applications while still providing the ability to introduce new features or hardware support through extensions. That being said, I'm sure you've noticed the asterisk by now. Argus is still a beta release, version 0.96 being the version included with the latest JetPack release. And so any part of the API is still subject to change until version 1.0 is released, currently scheduled for 2018. Any changes to the API between now and 1.0 will be documented in the release notes. Since the entire object and interface relationship revolves around the interface provider class, this is the first real code I'll present. As you can see, the interface provider class, which remember is inherited by all objects, contains just one single method, getInterface. This method takes an interface ID parameter and will return an instance of the requested interface, or null if the interface is not supported for that object. It's then the application's responsibility to cast the return pointer to the interface type being requested. The following example puts things together. The first box provides a snippet of the iRequest interface, both for reference and also to show the corresponding interface ID definition. The second box provides an example of acquiring the iRequest interface from a request object and calling a method using that interface. I mentioned earlier that objects may be destructible, which means that they must be explicitly destroyed by the client that created them. These objects simply inherit from the destructible class, which provides a single destroy method that is called to destroy the object. Now, some of you may want to call me out for saying earlier that objects do not have methods. So let me correct that statement now. GetInterface and destroy are the only two methods that will ever be called directly on an object, period. However, it's unlikely you'll ever actually call those methods directly from your application, since Argus provides two helpful utility classes. First utility is InterfaceCast, which wraps the getInterface method with C++ style casting semantics using the interface class name rather than the explicit interface ID. The second utility is a movable smart pointer for destructible objects, which simply destroys the wrapped object when it leaves scope. This example shows how the two utilities greatly improve code quality. On the left, without using these utilities, the code is plagued by awkward interface acquisition and excessive error checking that must also include explicit object cleanup. On the right, InterfaceCast provides a much cleaner syntax for interface acquisition that resembles typical C++ casting semantics. Note that this no longer requires explicit use of the IID request identifier, as this template simply uses the interface class name directly. Since the InterfaceCast may be used safely with null objects, we can also omit the initial check for null request object. Destruction of the request object is now handled by the unique object smart pointer when the pointer leaves scope at the end of this block. This is done regardless of early exits due to error conditions, so there's no need to ever explicitly destroy the request object. Well, it should be obvious by now that Argus is included with JetPack, specifically within the Multimedia API installation package. I'd like to point out that the Argus release includes much more than just the Argus API itself. The API headers, which are fully documented with Doxygen-style comments, are located in the include directory. Documentation, which includes both HTML reference pages as well as the full Argus specification, is located in the docs directory. Perhaps the most useful resource for new Argus developers, however, are the sample applications. We currently include 13 different samples, each focusing on small, directed use cases or Argus features. I'll describe some more of these samples later on, but the most basic of these samples, OneShot, is actually the source for the sample I'll be walking us through momentarily. Finally, we even include a reference Argus camera application featuring both GTK and console interfaces. This interactive application is a useful tool for experimenting and playing with many of the settings and features provided by Argus. Now that we've covered the Argus foundation and you know where to get Argus, let's introduce some of the core Argus objects and interfaces with a step-by-step walkthrough of a simple Argus application. This sample is broken into 6 steps. First, we establish a connection to the LIBARGUS driver. Second, we query the available camera devices and select one for use. Third, we create a capture session to capture from this device. Fourth, we create an output stream for the image output of the capture. Fifth, we create and configure a capture request. And finally, we complete the sample by submitting the request to initiate the capture. Again, this sample is taken from the OneShot sample that is included with Argus, which is a good place to get started following this webinar. First step for every Argus application is to establish a connection to the Argus driver. This connection is maintained by a singleton camera provider object, which is created using the static camera provider create method. This is the only function exported by the LibArgus shared library. The iCamera provider interface then acts as the root interface to the Argus API, providing access to camera devices and to capture session creation methods. Please note that I will be truncating interfaces throughout the example to show only what is needed for the sample. Please refer to the Argus headers and documentation for the complete interface definitions. Here we see the code that creates and establishes the driver connection by creating the camera provider using the static creation entry point, and the resulting object state below. The camera provider object itself is bright green, and the camera provider interface that provides methods wraps around that in the darker green. The camera device object represents a single camera device that is connected to the system and available for use with Argus. They are child objects owned by the camera provider and are not meant to be modified directly. Rather, they simply act as handles to the physical devices, and their camera properties interface reports the static properties and capabilities of the device. These properties can be read during initialization in order to select the desired device to use, and will also dictate what settings, features, and sensor modes are available for use at capture time when using the device. Here we call camera providers get camera devices, which populates a list with the devices that are available for use. For the sake of this example, we will simply use the first available device. Using a device initially means that it is used to open a capture session. A capture session is the heart of an Argus capture pipeline and maintains an exclusive connection to one or more camera devices. That is to say that many capture sessions may exist at any point in time, but each camera device may only be used by one session at a time. A capture session must be destroyed before its devices will be available for use by another session. Once created, the capture session is responsible for creating output streams, creating capture requests, adding requests to and managing the capture queue, and generating capture-related events for event queues. Capture requests may be submitted to a capture session using either a one-time on-demand request, which adds a single capture request to the queue, or may be set up to perform repeat captures such that the capture session will continually repeat the capture request until it has been canceled. Both methods also support burst variants, which atomically submit multiple captures to the queue as an ordered group. For this example, I'll be using the most basic one-time capture method, but I will be revisiting the other methods later. Here we create the capture session. This is done using the camera provider's create capture session method. we provide the device we have selected to this method, and it returns a new capture session object that now has exclusive control of that camera device. All capture requests need a destination stream for the output pixels, which is a role filled by output stream objects. Output streams are a little tough to explain on their own due to the fact that at this point in time, Argus uses EGLStreams exclusively for image output. This means that Argus output stream objects technically wrap an EGLStream and need to be connected to an EGLStream consumer in order to actually access the pixels written to the stream. I'll be discussing frame consumption and EGLStreams later, but for the sake of this initial example, we'll ignore the consumer requirements of the stream. Due to a large number of settings available for output stream creation, parameters are provided through a transient output stream settings configuration object that may be discarded after the output stream has been created. Here we see the two-step output stream creation. First, the output stream settings object is created and configured with a desired pixel format and image resolution. Next, this stream settings object is provided back to the capture session's create output stream method, where it is used to create the actual output stream. At this point, the stream settings may be discarded. The goal of every Argus application is to capture images, and all captures must start as a capture request. Capture requests are created by the capture session, and a single request object holds every single setting that is used to control the capture pipeline for a single image capture. Due to the vast number of settings that go into a request, many settings are divided into specialized child objects, which are in turn configured using their own interfaces. The source settings child is used to configure the settings of the camera device that is the source of the pixel data for the capture. This includes things such as the exposure time, gain, or active sensor mode of the device. The auto control settings child is used to control how ISP should or should not dynamically adapt the capture settings based on ISP generated statistics. For example, color saturation settings may be left entirely up to the driver, tweaked with a bias to shift the internally generated settings one way or another, or even overridden completely with an absolute color saturation provided by the application. While most request settings can usually be left with default values, every request must have at least one output stream explicitly enabled for output. Enabling an output stream implies that an image will be written to that stream upon completion of the capture, though further settings can be provided on a per-stream basis using the stream settings children. For example, post-processing may be disabled for a particular stream, or clipping rectangles may limit which area of the sensor image is included in a stream's output. Here we simply create the request and then enable our single output stream in the request using the enable output stream method. To make things a little more interesting, let's assume that we want to adjust the exposure time that is used for the request. This setting is still contained in the request object, but it must be set through the source settings child and the iSource settings interface it supports. Keep in mind that source settings control the camera device, and so the exposure time provided should be within a range that the camera device's properties and active sensor mode allow. Once the request is fully configured, the last step is to submit the capture request to the capture session. This sets the capture session and capture pipeline in motion. When the capture request begins processing, Argus compiles all of the request settings into a pipeline configuration that it uses to program the various hardware units and perform the capture. Once the hardware completes the capture, the output image is written to the output stream's EGL stream so that it may be acquired by the consumer. Again, I will be going into more details about the image consumption later in the presentation. Now that we've covered the very basic image capturing application, I'll introduce the Argus events and metadata components, and will present how these may be used to achieve greater application level capture control. I will also describe how Argus can evolve through the addition of extensions, and will introduce a few extensions that have already been added to expose TX1's ISP-generated image statistics. Argus's event system is implemented via three main interfaces. First, objects that are able to generate events support the event provider interface. This interface is used to query the list of event types that may be generated by this object, which changes depending on the type of object providing the events, and then an event queue may be created to receive some or all of these events on a polling basis from the event provider. If no events are available at the time of polling for new events, this operation may optionally block until new events are available. Despite the use of general event provider interfaces, capture sessions are currently the only object capable of generating events. The events they generate signal capture-related events. The error event reports that an error has occurred during a capture. The capture started event signals that exposure of the capture has started. And the capture complete event signals that a capture has completed. Every capture request that is submitted to Argus is associated with an increasing capture ID, which is returned by the capture session's capture method. This capture ID is included with every capture event and may be used to match events to the capture that generated them. All captures that are successfully completed by Argus are accompanied by capture metadata, which initially serves as a report of the capture settings that were used for the capture. While it may be tempting to just look at what settings were submitted with the initial capture request, this is not sufficient since the actual applied settings may not match the requested settings. The Argus implementation will always attempt to meet the requested settings as closely as possible, but various incompatibilities between request settings, or even just performance limitations, may require the driver to modify the settings in order to satisfy the request. In addition to a report of the effective request settings, capture metadata may also include image statistics generated by ISP or any other hardware or software statistics engine. Examples of this may include histogram statistics or face detection results. There are two different ways to read capture metadata from an Argus capture. The first uses Argus events, while the second allows the data to be embedded directly into an EGLStream frame to be read by the consumer. The first method I will introduce now, while the second I will save for the EGLStream discussion to follow. Since metadata accompanies completed captures, it makes sense that metadata is included with the capture complete events generated by the capture session. We can see this is the case by looking at the capture complete event interface, which provides the get metadata method to acquire the capture metadata object from the event. The following code provides a simple example of using events and metadata in order to print out various details about completed captures. This loop first waits for a capture complete event to be generated by the capture session by calling wait for events. This call blocks until a new event is available, at which time it moves the event into the queue to be accessed by the caller. You'll remember that event types can be selectively enabled on a per queue basis. And in this example, we'll assume that our queue was created to receive only capture complete events. So once we have the event and its interface, getting the metadata object is simply a matter of calling get metadata. This is then used along with the basic capture metadata interface to print out various details of the capture, such as its capture ID, the color saturation, and the exposure time. Reading metadata using events can be useful for an application that wishes to implement their own ISP and sensor control loop by modifying request settings for the next capture request based on the statistics of a previously completed capture. To do this, I've modified the previous example slightly. The first few lines that acquire the capture complete event remains the same, but instead of simply printing out the metadata details, this metadata is provided to a function that is responsible for modifying the request settings based on the statistics reported by the metadata of the previous capture. These new request settings are then used to submit a new capture request. Rather than provide a full example of modifying request settings based on the metadata and image statistics, which is a bit too involved for the time we have today, I will instead direct you to two samples included with Argus that do just that. The user auto exposure and user auto white balance samples each make use of histogram and pixel average statistics in order to adjust the exposure or white balance of the next request. When I introduced Argus, I mentioned that we are targeting an open and standard specification. For this to be successful means that the API must be suitable for adoption by a wide range of applications and hardware platforms. If we place features that are specific to NVIDIA hardware within the API, requiring other vendors to implement these features, it's unlikely that the API would gain much traction. Because of this, we have split Argus into the core API, which you've probably heard me say already, and extensions. The core API includes the basic capabilities that are applicable to any image capturing platform, while features that are non-standard, platform-dependent, or even just luxury conveniences will be considered extensions. An example of a platform-dependent extension would be the Bayer sharpness map, an image statistic generated by the TX1 ISP that provides sharpness metrics to help determine focus settings, while an example of a luxury feature is face detection. Argus's extension mechanism follows pretty closely with what other KHRONOS APIs do. First, extension headers and interfaces are added to the ext subdirectory of the Argus include path and are defined within the ext namespace. They are identified by unique extension name IDs, and a global camera provider query will return whether or not a particular extension is supported by the Argus implementation. Just because the driver implementation supports an extension, however, does not mean that it will always be available for use. For example, an implementation may report support for an extension to enable high dynamic range cameras through the global camera provider extension query, but this extension may not actually be available for use unless an HDR camera device is connected and opened for use by the capture session. In other words, the global camera device query can be used to determine if an extension is not supported, but the runtime availability of an extension may be limited by other factors that are unknown to the camera provider. Because of this, runtime extension support relies on the standard getInterface mechanism. If an object supports an extension, it will return a valid interface for that extension. Otherwise, it will return null and the extension is not supported. A couple extensions included with the JetPack release add some of the more advanced image statistics generated by TX1's ISP to the output capture metadata. The first I already mentioned, Bayer sharpness map, provides sharpness metrics across the image which may be used to determine which areas of the image are in focus or not. The second, Bayer average map, provides Bayer domain averages and clipping statistics generated by ISP. This image, which is a screenshot of a sample application that is included with Argus, shows an ISP processed image on the left alongside visualizations of the average and clip count metadata on the right. The bright pixels of the bottom right view correspond to areas of the image which have many clip pixels, in this case due to overexposure. A few other extensions are included, such as a defog extension to minimize fog effects, a sensor private metadata extension to provide generic access to proprietary metadata that may be embedded on a particular sensor device, and of course, face detection. This screenshot is another sample application included with Argus. Capturing images using Argus is a relatively simple process, but there are some important considerations to make when it comes to the performance and efficiency of your application. As we've already shown, capturing and processing images through the camera subsystem involves a linear pipeline across a few different hardware and software components. While each of these steps in isolation may be reasonably fast, the accumulated processing time across the entire pipeline may be comparatively large. In fact, the overall processing time from exposure start to image output generally spans multiple frame periods. Furthermore, some of these steps, such as the start of sensor exposure, may only begin at the start of a frame period. So if a frame period is missed and a new request is submitted just after a frame period has already begun, the new request will have to wait for a whole other frame before it can even begin exposure. So if a camera application is written to submit one capture request and then wait until that capture has completed before submitting another capture request, This leaves massive gaps in the processing pipeline for hardware to sit idly by as the capture is being processed elsewhere in the pipeline. For example, pixel data may be transferring over CSI while everything else remains idle. The solution to preventing these idle gaps in the pipeline is to ensure that the capture request queue always contains enough requests such that the Argus driver is able to perform multiple captures concurrently and saturate the pipeline. This leads to the next issue, however, which is how many captures are required to saturate the pipe. Is it 2, 5, 10? Unfortunately, this quantity may be dependent on a lot of factors that are not necessarily known by the application, so it can be difficult to determine. One approach could be to just keep a very large number of requests in the queue to ensure that the capture pipeline is saturated regardless of the specific system conditions. But this approach introduces its own problem. As we showed in an earlier example, image statistics may be used in a feedback loop to control the capture settings of future requests, such as for auto exposure or white balance routines. In this case, if the capture request queue contains more requests than can be currently processed by the pipeline, then multiple requests may sit idle before even entering the pipeline. This introduces an excessive delay between when the image statistics are returned and when the next capture request derived from those settings will be used. So it continues to be the case that we need to saturate the capture pipeline, but at the same time, we want to prevent excessive requests in order to minimize the statistics feedback delay to ensure more responsive settings convergence. The solution to this is to use the capture sessions repeat capture method. As I mentioned earlier, Argus capture sessions offer both on-demand, one-at-a-time capture requests, but also a repeat capture method which allows Argus to continually issue a given request until it is canceled. Since the Argus driver is aware of the number of captures that may be processed concurrently, however, this means that Argus will only keep as many captures in the queue as are actually needed to saturate the pipeline. This maintains ideal pipeline efficiency while minimizing the number of idle requests to ensure that statistics feedback loops are as responsive as possible. The capture request being repeated may be replaced by another call to repeat, or repeat captures may be stopped by calling stop repeat. When calling stop repeat, the range of capture IDs that were generated by the last repeated request will be returned. This slide updates the previous example of a stats-driven capture control loop to use the repeat captures method, with changes bolded. While unlikely, the use of repeat captures requests means that it's technically possible for more than one capture to complete between iterations of this loop. And so we handle this by ensuring we always use the latest capture complete event to update the request settings to maximize responsiveness. So far we've seen how Argus is used to capture and process images from a camera device. But we've ignored an important part of the question. Where do the images go and how do we use them? As I've mentioned before, Argus currently only outputs images via EGLStreams, and so must be paired with an EGLStream consumer. But what are EGLStreams and how do we consume images from them? In a nutshell, EGLStreams are an interrupt mechanism used to efficiently transfer a stream of images between two APIs, called the consumer and producer endpoints. EGLStreams internally provide buffer allocation, synchronization, state management, and metadata transport, leaving very few responsibilities for the client application. EGLStreams are an open standard defined within the KHRONOS ecosystem, and a number of EGLStream-compatible APIs already exist. Similarly, new extensions and API support is continually being added to expand the utility of EGLStreams. The full EGLStream specifications may be found on the KHRONOS website. There are a few existing EGLStream consumers that are typically used by Argus applications. The first consumer is OpenGL, or the embedded variant, OpenGL ES. OpenGL is a 2D and 3D rendering API that unleashes the raw rendering power of the Maxwell GPU. When this consumer is used, images from the stream are bound to texture objects, which can be used for rendering just like any other OpenGL texture would be used. This consumer is used by many of the samples for on-screen display of the camera preview stream, while some of the other OpenGL rendering features are used for metadata visualizations. The next consumer is GStreamer, which is an API used for constructing pipelines for multimedia applications. The GStreamer consumer is used along with Argus primarily for encoding video files from the camera streams. Finally, CUDA is an NVIDIA API that provides GPU compute capabilities. I will not be showing code examples of these consumers today, since this could easily fill an entire webinar in itself, but I urge you to check out the Argus samples for examples of how these are used. I will be providing a summary of the samples shipped with Argus, along with a description of the consumers they use at the end of this presentation. Besides the existing consumers I just mentioned, there's one additional consumer that was written specifically for the needs of Argus, and is actually included as part of the Argus SDK, and that is the generic EGLStream frame consumer. This utility provides some key consumer use cases for camera streams, namely JPEG encoding and native buffer compatibility. This utility API uses the EGLStream namespace, but borrows most types and design concepts from Argus, including the separation of objects and interfaces. Because of this, the frame consumer is highly integrated with Argus, and in fact it can be used with an Argus capture application without ever needing to call a single EGL function. So little to no knowledge of EGL streams is required to use this consumer. Using a frame consumer involves three components. First, the frame consumer itself must be created and connected to the stream using the static frame consumer create function. When used with Argus, this function may be provided the Argus output stream object directly, such that no EGL objects or function calls are required. If the frame consumer is ever used with an EGL stream not being produced by Argus, however, the EGL stream handle may still be provided instead. Once created and connected to the stream, the frame consumer's interface provides the ability to acquire frames from the stream. Acquired frames provide access to the image object associated with that frame, as well as frame details reported by the EGL stream. If you'll recall, however, I mentioned during the discussion about Argus metadata that metadata may be embedded within an EGL stream's frame. Therefore, whenever a frame consumer is connected to an Argus producer, the Argus capture metadata interface will also be supported by each frame, such that the Argus capture metadata object may be retrieved directly from the EGL stream frame. Finally, the image object contained by a frame provides different interfaces that can be used to access the underlying image data. In particular, the image JPEG interface provides an extremely simple method for JPEG encoding, which we will now use in an example. We ignored the consumer components in our sample walkthrough earlier, so this example goes back to fill in those missing details. New additions are bolded. Starting with the Argus output stream, we first create and connect the frame consumer to this stream. After issuing the capture request to the session, we can then call acquire frame on the consumer in order to acquire the new frame. This is a blocking call and will return once the frame is available. Once the frame is acquired, the metadata interface can be used on the frame to retrieve the Argus metadata embedded in the frame. Finally, the image is retrieved from the frame, and the image JPEG interface is used to encode and write the image to disk as a JPEG file. Including these additions, we have now walked through the entire one-shot sample and completed our first complete Argus application. Now, some of you may be wondering, are EGL streams really the only way to consume outputs from Argus? The answer to this is no, but with an asterisk. EGL streams do have limitations. They depend on EGL, they provide less control of the underlying buffers, they don't support complex buffer pipelines or use cases, and ultimately, they can only be used with APIs that support EGL streams. The best example of this is V4L2, which is still supported and used by many Jetson customers for custom image processing pipelines, but its lack of EGL stream support makes it impossible to retrofit Argus as the capture control API. So while it is true that Argus currently only supports EGLStream outputs, this is a temporary limitation. We are currently working on adding low-level or native image buffer output support to Argus, and intend for this to be available with the next beta release in the first half of 2017. Until then, we do have a temporary solution that will allow applications to use native image buffers with Argus, and this is the Image Native Buffer interface included with the EGLStream frame consumer. This interface provides the ability to copy EGLStream images acquired by the frame consumer to native NV buffers that are provided by the application, allowing the images to be used anywhere NV buffers are used today. That finishes up the instructional part of this webinar. But before I finish up, I would like to give a quick overview and description of the samples that are included with Argus, as I feel these are the best place for new Argus developers to get started. First sample I would recommend starting with, which is the one we use for the walkthrough today, is the one-shot sample. Two of the other samples I mentioned earlier, user auto exposure and user auto white balance, make use of both the histogram and Bayer average map statistics in order to dynamically modify capture settings to achieve target exposure and white balance convergence. The next few samples each provide usage examples of the different EGLStream-consuming APIs that I had briefly mentioned earlier. The OpenGL box sample uses the OpenGL consumer to render a camera stream onto a 3D spinning cube. The GST video encode sample configures a GStreamer consumer pipeline to encode an H.264 video file from a stream. And the CUDA histogram sample uses CUDA to calculate histogram statistics for each frame. The next couple samples use the OpenGL consumer to render visualizations of captured metadata. The first provides a visualization of the Bayer average map. The first provides a visualization of the Bayer average map average and clipping statistics, while the second highlights faces detected using the face detection extension. Two additional samples demonstrate the use of multiple stream outputs from a single capture request. The multi-stream sample makes simultaneous use of a previous stream that is consumed by OpenGL and rendered to the display, alongside a still capture stream which is used to write JPEG files. This sample also makes use of repeat burst capture requests so that the still stream is enabled for use only for a subset of the capture requests, while the previous stream is updated with every request. The denoise example provides a side-by-side comparison of the effects of enabling denoise processing. Both streams in the sample are consumed by OpenGL and rendered to the display, but denoise processing is disabled for one of these streams using per-stream request settings. Finally, we have two multi-sensor samples. The multi-sensor sample requires two sensors to be available, but the sensors are not required to be related in any way. This sample creates two capture sessions, one for each sensor, and uses one of the sessions for OpenGL preview, while the other is used for JPEG captures. The sync sensor sample, on the other hand, requires the use of a stereo or synchronized sensor board. This sample opens the stereo pair with a single capture session and consumes both streams together with CUDA in order to compute the stereo disparity between the two streams. This brings us to the conclusion of this webinar. I'd like to thank you all once again for watching. A recording of this presentation, as well as a copy of these slides, will be made available on the original registration page for this webinar. We are repeating this live webinar once more later today, however, so these may not be available until after the broadcast.